Bismillahirrahmanirrahim. Welcome to another module of the course, Mathematical Foundations for Machine Learning and Data Science. In this course module, we will continue our discussion on operations on vectors. We will talk about span of vectors, what do we mean by linear independence and dependence between vectors, what are the basis vectors, and what do we mean by orthonormal vectors. So let's start with span. Before I formally define span, let me quickly review what do we mean by linear combination of vectors. So what we studied earlier, that if you have two vectors, say a1, a2, that belongs to Rn, and say you have two scalars, beta1, beta2, that belongs to R. So we define linear combination of vectors as beta1, a1 plus beta2, a2. So this is a linear combination of vectors a1 and a2, where beta1 and beta2, they are scalar coefficients. And what we know that this also represents a vector that belongs to Rn. Okay, before I define span formally, let me quickly talk about this linear combination geometrically. So we want to find out what do we mean by linear combination graphically. So for convenience, let's start with R2, and say if I'm in R2 and I take a vector, say I take a vector a1, right, and I take another vector, say let me take that vector, say somewhere, so this is, I call it a2. And if I ask you that what are possible linear combinations of a1 and a2, so you're free to choose beta1 and beta2. So what are the possible linear combinations of these two vectors? That would be, in fact, this whole line that's passing through a1 and a2. So this, all of these points. So a1 represents this point, a2 represents this point, and we know that all of these points on this line, so they are beta times a1 plus beta times a2. Okay, let me take another example. Say I again take the same a1, and now we take a different a2. Okay, the question here is, what are the possible linear combinations of a1 and a2? So you're free to choose again beta1 and beta2. This should be beta1 and this should be beta2. So since these two vectors, so in the previous case, the red one was along the same, was collinear with the blue one, but here, so the linear combination of red and blue would span, I should not use the word span, the linear combination of this red and blue would cover the whole two-dimensional space, right? So in fact, you can say that any point in R2, say this point in R2 or this point in R2 or this point in R2, so can be expressed as a linear combination of a1 and a2. So I would say, so if I define a set that is a linear combination of these two vectors a1 and a2, that set would be the complete two-dimensional space R2. Okay, so let me also try to explain this using a three-dimensional setting. So let me use MATLAB. In 3D setting, we take one vector first. Say we are in three-dimensional space, and we take this vector A. And if you want to find out what are the linear combinations of this vector, since we only have one vector, the linear combination would be only scaling. We don't have any addition. So the linear combination of this vector A would be, in fact, the whole line that's passing through this point A. So let me add another vector to this three-dimensional space. Say we add another vector. So now we have two vectors A and B, right? So just to show you that they are not, so A and B, they are not on the same line, right? So here, right? Now if I want to find out what are the possible linear combinations of A and B, so let me draw all of the points that represent their linear combinations. So in fact, this whole plane, this two-dimensional plane, so this represents all the points which are possible linear combinations of A and B. So this is extending from minus infinity to infinity. This is infinite dimensional, infinite two-dimensional plane. Now let me add another vector. So I have added another vector, and let's talk about this vector C, right? So if we see this C vector lies in the same plane, in the plane that is the linear combinations of A and B. So that means now if I want to find out what are the possible linear combinations of A, B, and C, I will get the same plane, right? Okay, but if I add one more vector, and this is D, right? And if we see D, so D is not on the plane formed by linear combination of A and B and C. So now if I find out the linear combinations of A, B, C, and D, all possible linear combinations of A, B, C, and D, I will get the complete three-dimensional space. So can you see the connection here? So when we added C, we still got the two-dimensional plane because C was on the same plane as that plane was formed by linear combinations of A and B. So I can say since C was a linear combination of A and B, so that's why we did not get an extra dimension when we added C. And when we added D, since D was not a linear combination of A and B, and when we take linear combinations of A, B, C, and D, we get the complete three-dimensional space, or dimension of the space increased by 1. Right? So if you understand these basic concepts, then we can build on these, and we can talk about the formal definitions of span, linear independence, what do you mean by basis. Let's define span now. So span as all possible linear combinations of vectors is called span. So if we're given, say, vectors a1, a2, say k number of vectors, and each vector belongs to Rn. So, and we take a scalars beta 1, beta 2, beta k, they are scalars. So we define span of a collection of vectors a1, a2, ak as all possible linear combinations. So as a set of points which contains set of vectors beta 1 a1 plus beta 2 a2, beta k ak, and where each beta belongs to a set of real numbers. So this is the definition of span, right? Or in words you can say, if someone asks what is span is span of a collection of vectors is a set of all linear combination of vectors. Okay, so what we talked earlier, that say if we're in R2, say we're in R2, wait, so let me shrink it a bit. So if I take two vectors, say A1, and I take another vector, say A2, the span of A1 and A2 would be R2. But if A1 and A2 are collinear, as we had in this case, so in this case the span of A1 and A2 would be a line that belongs to R2. And similarly, when we talked about 3D setting, when we took two vectors, the span of the two vectors that were not collinear, the span of those two vectors were the span of those two vectors represent a plane, right? So similarly, if you have maybe you can talk about, say we're in R3, right? And if we take two vectors and they are not collinear, or they're linearly independent. We'll talk about linear independence very shortly. So if two vectors, they are linearly independent, the span of those two vectors would represent a plane. And if we take three vectors, and if these three vectors are linearly independent, what we get is the whole R3. Right? So this is span. Okay, now let's talk about linear independence. Linear independence means that if we have a collection of vectors, or a list of vectors, or a set of vectors, we say such collection is linearly independent if any vector in the set cannot be expressed as a linear combination of other vectors in the set. So let us define first mathematically, and then we will try to interpret the definition. So we say we have a collection of vectors, again A1, let me use, say if we have vectors A1, A2, AK belongs to Rn. So if we have scalars, say beta1, beta2, beta k that belongs to R. So these k number of vectors are linearly independent if beta1 A1 plus beta2 A2 plus their linear combination is equal to 0 if and only if so beta1 is equal to beta2 is equal to beta k, and that is equal to 0. If all the betas are 0, only then the linear combination is equal to 0. Otherwise the linear combination is not equal to 0. So there is no non-zero beta for which the linear combination is equal to 0. Okay, how do we interpret this definition as that one vector cannot be expressed as a linear combination of other, right? Say for example, if beta1, beta2, beta k, they're not 0, right? And this linear combination is equal to 0, and that simply means I can write, say beta1 A1, in fact any of the vector is equal to negative of beta2 A2 plus beta k AK, and if I divide by beta1 on both sides, I get, say beta1 here and beta1 here. So if this holds for non-zero betas, then I can write any vector as a linear combination of the remaining k minus 1 vectors. So that's why if this holds, if and only if, when all the betas are 0, then we say, and this collection of vectors A1 to AK is linearly independent. So we also note here that the linear independence is an attribute of a collection of vectors. Okay, let me also maybe a couple of examples. Say if we have a collection of vectors that contains only one vector, right? So if you have a list that only contains, say, a1, so since we only have one vector, this list is linearly independent. And if we have a list in which we only have zero vector, so if we have a list that contains zero vector, so that list is for sure linearly dependent. So zero vector in any list, the list is linearly dependent. So maybe let me also talk about one more example. Say we take a vector in three-dimensional space. Say we take very simple vector 1 minus 1 1, and we take another vector, say 1 minus 2 3, and we take another vector c, which is minus 0.3 1.5 minus 2.7, and we note here that the linear combination, you can find beta 1 is equal to 1.2, beta 2 is equal to 0.9, and beta 3 is equal to 1. So their sum is equal to 0. If the sum is equal to 0, the betas are non-zero. We say a, b, and c, they are linearly dependent. And if we want to show this graphically, that simply means that this is a, this is b, and this is c. So they all lie in one plane, and therefore they are linearly dependent, since C is a linear combination of A and B. This blue plane is a is a set of all linear combinations of A and B, that is span of A and B. And when we talk about this vector C is in the same plane, and therefore it is a linear combination of A and B. In fact, C is minus 1.2a plus 0.9b, right? And therefore A, B, and C together is they are linearly dependent. It is not easy to check linear independence or dependence by inspection, and we'll talk about one algorithm in the next module which we can use to check the linear independence of a given collection of vectors. So let's talk about some of the implications of linear independence. So okay, so maybe the first implication would be that if we have a list of vectors that is linearly dependent, and if we form a superset that contains that list of vectors, that superset would be obviously linearly dependent. So we can say if list of vectors, a collection of vectors, is linearly dependent, so superset of vectors, so superset of list would be also linearly dependent. So opposite of this would be if you have a list that is linearly independent, if you take a subset of this list, that means you remove some of the vectors from the list, so that would preserve a linear independence. So subset of list is also linear independent. So, or we can say simply means removing a vector from linearly independent list preserves linear independence. Another implication would be if you have a collection of linearly independent vectors, and you can represent any vector as a linear combination of linearly independent vectors. That representation of a vector in terms of linearly independent vectors is always unique. So what do you mean by this? So say you have a vector, say that B belongs to Rn, and we represent B as a linear combination of linearly independent vectors. Say B belongs to Rn, and you have a collection of vectors a1, a2, ak, that also in Rn, and this vector B can be represented as a linear combination of these k number of vectors. So we can say beta 1 a1 plus beta 2 a2 beta k ak. Then this beta 1, beta 2 and beta k, so they are unique for any given B. If B can be represented as a linear combination of linearly independent vectors, then that representation is unique, right? Or you can say these beta 1, beta 2, beta k are unique. Now I'm going to use this unique representation using linearly independent vectors to introduce the concept of bases. So before I formally define bases, let us quickly review the concept of independence dimension inequality. That simply means, let me pose a question here. Right? Say if I have k number of vectors a1, a2, ak, and what we know that they are linearly independent, so we say they are linearly independent. And if I ask you a question that what is the maximum value of k you have, what's the maximum value of k you can have such that linear, as you know that they are linearly independent, we try to connect with what we have discussed earlier. So if we are in two-dimensional space, the maximum number of linearly independent vectors you have is 2. If you are in three-dimensional space, the maximum number of linearly independent vectors is 3. So we can say number of linearly independent vectors in n-dimensional space would be k. K should be less than or equal to n. And this is in fact called independence dimension inequality, that maximum number of linearly independent n vectors is n. Right? So we can say the formally what we can define is, so a list of vectors in Rn can have at most n elements, and in fact these n elements are called bases of Rn. So now we are all set to define what do we mean by bases. Let me first define bases. So we say we define bases a collection of n linearly independent n vectors. So n vectors means they belong to Rn, is called bases. So why do we call these vectors as bases? The overall idea is that we can use these bases, these n number of linearly independent vectors, to represent any vector in Rn. So we can say if we have, say, a1, a2 and ak are, sorry, in fact an linearly independent and each belongs to Rn, so they are linearly independent, the n number of vectors. That simply means that we can represent any vector B belongs to Rn can be represented the important thing is uniquely. As B is equal to beta 1 a1 plus beta 2 a2 plus beta n an, and for given B, these beta 1, beta 2, beta n are unique. So what does beta 1 quantify? Beta 1 quantifies the contribution of a1 in B. And say when we talk about Rn, the standard unit vectors, they are bases, right? So they are linearly independent, they are bases, and any vector B that has components b1, b2, bn, it's going to be written as b1, sorry, e1 plus b2, e2. This is just one example of representation of B when e1, e2 and en are chosen as basis vectors. In fact, there are an infinite number of choices to choose these n number of linearly independent vectors for representation of vectors in Rn. So once we choose these bases, the next step would be how to determine these coefficients beta 1, beta 2, beta n, and that quantifies the contribution of each of the bases towards given vector B. So this finding of these coefficients can be simplified if we choose bases with some nice properties, and among those properties, one of the property is the orthogonality of the basis functions, or if we choose the basis functions to be orthonormal. Let's talk about the concept of orthogonality and orthonormality. So we begin with defining what we mean by orthogonality or orthogonal vectors. So we say the two vectors, say a1 and a2, they are orthogonal if their inner product is equal to 0. That simply means a1 and a2 are not 0, but a1 a2 inner product, that is a1 transpose a2, is equal to 0. Or this can be also, this is also written as equivalently a1 is perpendicular to a2, or the angle between a1 and a2 is equal to 0. So these are two different notations that are used to define orthogonal vectors. So this is defined for two vectors, but how do we define orthogonality for a collection of vectors? Say we say a list of vectors a1, a2, ak. So these vectors are mutually orthogonal take an inner product of any of the vectors, say AI, with any other vector except for AI, so what you get is 0, and this is for when I is not equal to j, right? So if this condition holds, we say vectors a1, a2, ak, so they are mutually orthogonal. Okay, now let's talk about what do we mean by orthonormal vectors. If the vectors in the list are also unit norm in addition to mutually orthogonal, we say the vectors are orthonormal. So we can say orthogonality if the vectors are orthogonal and also unit norm, we say together the vectors are orthonormal. So for a list of vectors a1, a2, ak, if the vectors are orthonormal, it means you take inner product with ai with aj, so what you get is 0 when I is not equal to j, and since each of these ai are unit norm, you get 1 when I is equal to j. So this is a formal definition of mutually orthonormal vectors. Now we can also talk about the linear combination in terms of orthonormal vectors. So what we also note here that orthonormal vectors are linearly independent by definition. They are linearly independent. Why are we so much interested in these orthonormal vectors? To answer this question, let's talk about representing any vector in Rn as a linear combination of orthonormal vectors. So say we take a vector b and we represent this using k number of orthonormal vectors a1, a2, ak. This is a representation of b in terms of orthonormal vectors. So what we know that orthonormal vectors are linearly independent. So beta 1, beta 2, beta k, so they are unique. So how do we find beta 1, beta 2, beta k? So the question is how to find, say, beta I. Due to orthonormality, we can find this beta I by simply taking inner product of vector b with ai, or by projecting b on ai. That is, if you project b on ai, what you get is beta I. Okay, to show this, let me substitute this representation of b here in the inner product definition. I can write b1 a1 plus b2 a2 plus beta k ak, and you take inner product of this with, say, ai. Say, and since when you take inner product of this with ai, what you get is beta 1 a1 transpose ai plus beta 2 a2 transpose ai, and so on and so forth. And since ai is orthonormal, inner product of ai with any a1, a2, ak would be 0, except when a1 when we have AI in this combination, so what you get is in fact beta I. So beta I, AI transpose AI, which is 1, since AI is unit norm, so you get is beta I, right? And therefore we can use simple inner product to find these coefficients beta 1, beta 2, beta k. If k is equal to n, since we are in Rn, so a1, a2, an, if they're orthonormal, they are called orthonormal bases. And we stop here, and today we have talked about span of vectors and the concept of linear independence, which we use to introduce basis vectors, and finally we have talked about orthonormal vectors. Thank you very much for your time.